Hi everyone, my name is Raquel Ortasun and I'm the Chief Scientist at UBLTG as well as a professor at the University of Toronto. Today, I will cover holistic understanding for self-driving, both in the context of data that has been captured by the fleet and offloaded to the data center, as well as in the context of real-time reasoning that needs to be done online in the vehicle to drive safely and smoothly to its destinations. Let's start with offline works. Modern self-driving vehicles are equipped with a plethora of sensors, including high-definition cameras, LiDAR, radar, ultrasonics, microphones, etc. Each self-driving vehicle typically captures more than 1 terabyte of data every day. Another question that arises is, what can we do given the fact that fleets of vehicles are typically in the hundreds these days, but will be in the thousands or millions soon into the future? In this part of the talk, I will show how to address the storage issues that arise because of the extreme large scale that we have in self-driving. I will then show how to intelligently access the data to retrieve important video snippets or perform question answering. Finally, I will touch on how to use this amazing data to perform realistic sensor simulation with very little domain gap with the real world. Let's start with the storage. A self-driving car acquires a massive amount of data every day. A single Velodyne sensor produces over 3 billion points an hour, translating to a terabyte of data every day. A suite of cameras can acquire over 2 terabytes of data every day as well. This amount of data is really expensive to store, so we need good compression algorithms to reduce the storage requirements. This can include both lossy as well as lossless compression, but today I will mostly talk about lossy compression. The unique aspect of compression in the self-driving setting is the rich multimodality of our sensors. Not only do we have multiple cameras capturing the video, we also have LiDAR strips as well. We build our work on top of entropy coding. A key concept in information theory is that the better we are able to predict the probabilities of a set of symbols by allocating fewer bits for frequent symbols and higher bits for less frequent ones, the better we can compress the distribution. The practical implementation of this idea is in the form of entropy coding, which is a lossless compression process that takes as input a set of symbols and encodes it into a bit stream. Entropy coding algorithms generally require a probability model to approximate the true distribution of the latent symbols. The better this model can predict the symbols with high probability, the lower the entropy and the smaller the number of bits required. Our compression approaches use neural networks to learn the distribution over images, video, and LiDAR. We first talk about a compression algorithm we designed to compress stereo images. The stereo images are typically present in the frontal cameras of self-driving cars. They are also present in other settings such as drones or 3D movies. Our approach is based on a key insight. The first image should improve the reconstruction of and reduce the bitrate of the second image in the stereo pair. We do this by adding parametric skip functions to do dense disparity warping between the encoded-decoded feature maps of the two images. We also reduce the joint bitrate with a conditional entropy model. Our final approach obtains a 10 to 50% reduction in the joint bitrate compared to single image compression approaches and video compression baselines. While stereo image compression compresses an image pair from two cameras at a single snapshot in time, each camera itself also captures the visual scene at high frequency, producing temporally related image sequences. Hence, we develop an algorithm for compressing monocular video. Unlike stereo image compression, video compression has been extensively explored with deep learning. However, many of these learning-based approaches contain complex architectures or autoregressive dependencies that are not ideal for practical use. In contrast, we develop a very simple entropy-focused video compression algorithm. Unlike previous works and video codecs, we do not do any explicit transformations across time, such as motion compensation or residual coding. Instead, we encode every frame independently with an image compressor and then fit a super lightweight and a non-autoregressive entropy model between frames. We additionally develop an internal learning extension that allows us to do additional encoding fine-tuning during inference. The end result is we achieve similar state-of-the-art performance with prior works while being much faster, and that's much more practical. Another important sensor for self-driving is, of course, the LiDAR, which produces billions of points an hour. We have developed a novel approach for LiDAR compression, which is presented at this GeoSim. A key challenge of representing LiDAR is the sparsity and non-uniformity of point clouds. Towards this end, we first serialize and quantize the point cloud as an octree. The octree contains intermediate nodes storing the child occupancies, as well as leaf nodes. The nodes contain numerous patterns across ancestors that can be exploited. We designed a novel tree structure entropy model, parameterized by neural nets, to exploit these patterns and reduce the octree bitrate. Our final approach is really fast and has a 10 to 45% improvement over the state-of-the-art methods, such as Google's Draco. Thus, we show that by deriving dedicated entropy coding algorithms, we can reduce the storage requirements for the sensors significantly beyond the state-of-the-art. We have also developed techniques to compress HD maps, or high-definition maps, improving the self-driving car. Unfortunately, I don't have time today to show you all this cool work, so please read our papers if you're interested in map compression. Now that we have discussed efficient storage of our self-driving data, let's move on to the problem of efficiently leveraging this data through data understanding. A powerful log understanding system has many applications within self-driving. First, log search enables the retrieval of thousands of variations of interesting scenarios, useful for stress testing and autonomous system in simulation. Second, automated log tagging enables developers to automatically find common causes of failure by visualizing the tags most correlated with the system's failure. Finally, some approaches to log understanding can additionally provide a learned semantic space for driving scenes that can be used to cluster common scenarios and, more importantly, ensure that current training and evaluation datasets cover the full space of real-world scenarios rather than narrow fit into a particular subset. Let's consider some potential approaches for building a log understanding system. The simplest option is to use humans to manually tag the scenes with descriptive annotations that can later be used for log retrieval and analysis. While this approach can be effective on very small datasets, it does not scale to self-driving datasets containing millions of miles, as it is far too expensive and time-consuming to use. Alternatively, the outputs from the onboard perception system can be reused to heuristically reason about different scenarios based on the detections over time. Unfortunately, this approach requires extensive engineering, often returns noisy results, and cannot generalize to many scenarios which require reasoning beyond more than the detected actors. Finally, we could consider building a natural language Q&A system. While in theory, natural language can express questions related to any attribute in the scene, it also introduces extra complexity and is therefore ill-suited for the real-world setting of log understanding. Motivated by the shortcomings of these approaches, our goal is to build a system which takes only raw sensor data as input, learns a single model for a complex and varied set of questions, yet uses a structured format to avoid the complexity of natural language queries. To achieve these goals, we introduced the novel task of structured question answering for self-driving. Given raw sensor data from a self-driving log, our task is to answer structured questions represented by three components: QX, QR, and QP. QX is the question attribute, which can be any continuous or discrete attribute in the self-driving scene. Examples of these attributes are vehicle actions like turning or map attributes like intersection types. QR is the question's region of interest. As an example, the user can set QR to be the region in front of the SDB, shown in the figure on the right. Finally, QP references to a pooling function, which specifies how values are pooled across the region of interest. Depending on the context of the query, we may either want to sum or pool values across QR. This task introduces many interesting challenges. First, sensory inputs can be noisy, especially at long range, making it difficult to accurately recognize many attributes in the scene. Models must also support a diverse and complex attribute set, which can be both related and unrelated. Additionally, these attributes can be both continuous and discrete. It is also critical that our model can efficiently scale with the number of questions so that our system can be used for real-world log retrieval. Finally, our model should support explicit spatial reasoning about the given region of interest QR. Our approach is carefully designed to overcome these challenges. We learn a single data log embedding from raw sensor data used to answer our queries. Attributes are represented by learn embeddings, allowing similar attributes to learn similar attribute representations. Both embeddings are combined together with a simple element-wise dot product. And our design ensures that our model can be used to efficiently answer many questions, since log embeddings can be pre-computed once and cached for future queries. Finally, our embedding maintains spatial dimensions so that the question's regions of interest are pooling functions can be applied directly. Let's now showcase some examples of attributes QX we want our system to be able to reason about. First, we consider the actual density of the scene. For any spatial region, we can count the number of vehicles or pedestrians. Here we show an example of a particular dense scene with many vehicles and also many pedestrians. These scenes can be particularly interesting for the evaluation of prediction and motion planning models. We also consider the actions performed by any agent within the scene. This includes whether each vehicle is stopped, braking, parked, lane changing, or turning. For pedestrians, we consider actions like walking along the sidewalk and crossing the street. In addition to actions, we consider a diverse set of labor interactions, including stop for, braking for, and yielding to other actors. Along with these discrete attributes, we also consider continuous attributes of the scene, such as each vehicle's current speed. And finally, we consider questions which relate to the map topology. Next, we will describe our model, which can efficiently answer questions related to this diverse set of scene attributes from only raw sensor data and HD maps. Our log embedding network learns a universal spatial embedding for each timestamp. The fully convolutional network takes a series of voxelized data strips and a rasterized HD map and produces an embedding. Importantly, our embedding is spatially aware and maintains the original spatial dimensions downsampled at a rate of R. We use this embedding E to answer all the questions. Now imagine we are given a structured question which encodes, is there a vehicle turning left in front of the SDV? First, we encode the question attribute QX, which in this case corresponds to a predefined left turn attribute. To represent the attribute, we simply look up its corresponding row in a learnable matrix K. Our answering module takes both the universal embedding E and the attribute embedded as input. Using a simple element-wise dot product, we obtain a spatially aware answer map, capital A. Finally, we pull results over the spatial region of interest. In our example, this corresponds to the region in front of the SDV. Results are pulled using a pooling function specified by the question, returning an answer, lowercase a. Our approach is trained end-to-end to minimize supervised query loss across the 15 attributes described earlier. Our model can also be extended to handle compositions through the use of compositional functions. Compositional functions take a set of spatial answer maps from multiple attributes as input and returns a new answer map. Compositions enable our model to naturally handle more complicated questions that relate to multiple attributes. For example, finding scenes with vehicles turning at a three-way intersection. As shown in this example, we also use compositional questions to break down the recognition of vehicle actions and interactions into two simpler subtasks. First, recognizing the existence of a vehicle at a particular location through vehicle density. And two, reasoning about the vehicle action condition of a vehicle being present at that location. Let me now play you a video.
In this visualization, we show the rasterized map given to the model as input. On top of the map, we overlay the ground truth actor bounding boxes, which are not given to the model. First, we show a video with 2 seconds of context surrounding the scene. Our model is trained to answer questions relating to the center of the snippet. Question 1, is there a vehicle turning left in the intersection? Both our model's answer and the ground truth answer are yes. We can see the vehicle our model classifies as turning left in yellow. Question 2, how many pedestrians are in the intersection? To obtain an answer, our model first regresses a density at each spatial location. Here we overlay our pedestrian density estimates at each spatial location. By pooling over the intersection region, we obtain our model's answer. Our model, 17.8, ground truth, 17. Let's move on to another scene. First, we'll show 2 seconds of context. Question 1, is there a vehicle braking for another vehicle behind the self-driving vehicle? Both our model and the ground truth answer yes. Question 2, how many vehicles are in the entire scene? Once again, we overlay our model's density predictions at each location. We sum the values over the entire scene to obtain our answer. Our model, 48.6, ground truth, 45. Let's move on to a final scene. Again, we'll show 2 seconds of context. Question 1. What is the maximum vehicle speed in this scene? We can answer this with a compositional query. First, we compute the vehicle speed at each spatial location. Next, we compute density at each spatial location and use a threshold to mask out regions without vehicles. Finally, we multiply the 2 answer maps and max pool over the scene to obtain our final answer. Our model, 15.9 meters per second, ground truth, 15.8 meters per second. Next, we'll show a failure case of our model. Question 2, is there a vehicle performing a right lane change anywhere in the scene? Our model answers no, while the ground truth is yes. Let's rewatch the scene to see why this question is difficult for our model. Pay close attention to this actor, as it will perform the missed lane change. Notice that for some frames, the actor is fully occluded. Also notice that at time t equals 0, the vehicle is just at the beginning of changing lanes, making this classification more difficult. If we ask the same question 1 second later, our model correctly answers that the vehicle is changing lanes. Thanks for watching our video.
Next, we test our model in the retrieval setting. For example, in the first row, we show logs that our model retrieves when asked to find examples with more than 10 vehicles around the SDB. In the second row, we show visualizations of retrieved scenes that have a 3-way intersection directly in front of the SDB. Finally, in the last row, we show examples of other actors turning in front of the SDB. We compare our approach, which learns a single embedding for all questions, against one where the embedding is separated by question category, each outputted by an independent trained model. Our results show that for small embedding dimensions, our model clearly performs the separated embedding approach for questions related to both continuous and discrete attributes. In fact, we found that the separate model was unable to learn to answer density questions in this limited data setting, resulting in extraordinarily large errors. As we increase the embedding dimension to 16, we continue to see our approach significantly outperforms the separate approach. These results showcase that our approach effectively learns to use the dimensions of the embedding space better than using prior human knowledge to divide embedding memory based on, for example, question categories. Finally, given enough memory, both approaches perform similarly. We can see a slightly higher performance in the separated model, likely due to the fact that it has 4 times more model capacity, and thus this is not necessary for comparison. In a real-world setting, the questions that need to be supported by a self-driving Q&A system will grow as requirements change and new supervised data becomes available. Ideally, models should support continuous learning, in which new questions attributes are trained on top of a learned model. Therefore, we also explore whether overload embeddings can boost performance in this setting when a new scene attribute is added with limited supervision. For this experiment, we selected a single attribute shown on the x-axis to remove from the first stage of training. Then we add the held out attribute with only 10% of the original data, simulating a limited data setting and continue training. In blue, we show the performance of a baseline model trained only on the held out attribute. In red, we show the performance of our continuous learning model after training. For additional context, we also compare against a model trained on 100% of the training data, 10x more data than the models in blue and red. Our model always outperforms independently trained baseline, and for some attributes, it has up to 32% relative improvement. For turns, braking, and lane changes, our model performance is actually closer to the performance of a model trained on 100% of the data than the independently trained baseline. Finally, we show a DSDNet visualization of the universal embedding space. Each point corresponds to embedding vectors at the spatial locations with vehicles. We color each point with the primary action of or interaction of that vehicle. 3 dominant clusters are apparent: vehicles keeping lane, stop vehicles, and parked vehicles. We also see smaller clusters appear for more rare actions such as left turns and right turns. This visualization demonstrates that the embedding captures the high-level semantics of each spatial location. In conclusion, in this work we introduce the new task of structured question answering for self-driving. We propose an approach capable of answering a variety of complex set of questions relating to real-world self-driving scenes. Our approach learns a universal embedding for all questions with strong generalization properties demonstrated in the continuous learning setting and a semantically meaningful latent space. There are many extended future directions to explore. Future models should explore leveraging information from more sensors of the DSDB, including the cameras and radar captured by the vehicle. Models should also explore more complicated architectures to enable better spatial-temporal reasoning. Finally, we are excited by the prospect of learning a set of compositional functions in order to improve the performance of the systems on computational queries. Tons of things to do. Along with compressing the data we collected and mining the data for key events, we can also use larger scale data to create new data via simulation. As Richard Feynman once said, "What I cannot create, I do not understand." And simulation, in particular sense of simulation, help us better understand different self-driving scenarios and how to evaluate autonomy systems. Before we discuss sensor simulation, let's discuss briefly the different ways we evaluate SDVs and the value sensor simulation provides. The self-driving industry uses a combination of 3 different approaches for evaluating and testing SDVs. First, there is structured testing, which tests the SDV under a set of reproducible scenarios. This is typically done at a test track facility. This test setting is considered high fidelity, since we can evaluate the full autonomy system and hardware of the car in the real world on a particular scenario. We also consider this testing to be reactive. As the SDV perceives the scene and performs a maneuver, the other agents in the real world can respond to its behavior, and the sensor observations are accordingly updated. While effective, structured testing currently has many limitations. It's difficult to test extreme or dangerous situations, such as high-speed avoidance maneuvers. Additionally, larger-scale testing is simply impractical. We can also evaluate the SDV on pre-recorded real-world data. This potentially provides a more realistic setting for urban driving scenarios compared to structured testing. However, this situation is not reactive. The sensory data and other actor behaviors are not updated according to the SDV's actions. It's also still difficult and potentially unethical to collect and test safety-critical cases at scale. The third method is simulation. While simulation systems have a domain gap with the real world, simulation has some significant advantages. The agents and the environment in simulation can be reactive. Simulation allows testing any safety-critical scenario easily. And excitingly, simulation has the potential to be scalable. Not only can we perform millions of different evaluation tests, we can also use simulation for training different autonomy algorithms. We now review the self-driving vehicle autonomy system and how we can inject simulation for evaluation. Every fraction of a second, the vehicle senses the environment. The perception system is then responsible for estimating where the objects are in the scene. The prediction system detects the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning model focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicles will do in the next few seconds. Traditional simulators only simulate bounding boxes or trajectories, enabling only motion planning evaluation. This is the typical approach in industry due to ease of running and relatively low overhead. It makes the assumption that the self-driving stack is modular and just uses active dynamics for traffic simulation. End-to-end closed-loop testing of the full autonomy stack requires going farther than just simulating bounding boxes and trajectories. We need to have a complete simulation system that models the real world accurately. To build such a complete simulation system, we need to estimate the dynamic state of the environment, where we have actors including vehicles, pedestrians, and cyclists, construct the geometry of both the static environment and the dynamic actors, and finally simulate the sensor observations that the SDV might receive on that particular scene. Here we show a LiDAR sensor on one of our vehicles. LiDAR generates a 360-degree 3D geometry point cloud of the scene, along with information about material reflectance, objects through intensity. I will now discuss how typical simulation environments simulate LiDAR through standard graphics, and how we instead use real data to simulate LiDAR. Recall that we have millions of miles captured with these petabytes of data, and this is going to enable us to create simulation at scale through scene understanding. Standard graphics, such as simulation based on game engines like Carla and EarthSim, simulate LiDAR by designing 3D assets by hand, building a virtual world, and then physics rendering the LiDAR. The advantage and disadvantage of graphic-based engine simulation is explicit world and physics modeling from the ground up. This allows for total control of the world and precise definition of all the assets. But unfortunately, it is expensive to create these assets as they are done by hand. It is not scalable to have virtual worlds for the numerous cities we want to test, and the simulated LiDAR is typically unrealistic. Our work at this year's CVPR, called LiDARSim, leverages both graphics and real-world data along with machine learning. LiDARSim builds assets at scale using a fleet of self-driving cars with standard sensors, and then uses physics with machine learning to generate realistic LiDAR simulations at scale of new potential scenes. I will now discuss in more details the different components of LiDARSim. LiDARSim leverages millions of real-world miles collected by our fleet of self-driving cars to help build virtual worlds for autonomous vehicle testing. On the right, you can see the reconstructed background scene of an intersection and a collection of the different dynamic objects created from LiDAR data. Here we show how LiDARSim generates realistic backgrounds. We record real LiDAR data by driving in an area and remove moving objects. We aggregate and align the LiDAR, combine across multiple trajectories, and create a mesh surface representation. A similar process is done to generate dynamic objects. We utilize a symmetric prior to get a complete shape of an object. Leveraging real data allows us to inject the diversity of objects seen in the real world into LiDARSim. From left to right, we can see cars with open hood or trunk, bicycles on top of the car, flatbed trucks with construction cones, and trailers with extended cars. Making sure we can detect these rare objects as vehicles is important, and by leveraging real data, we can simulate more situations that are in the long tail. You often don't see this diversity from other 3D assets or CAD model datasets that are available out there. Once we generate our assets, we can place them in a scene configuration, just like in a video game. We now have scalable and diverse scenes. We then perform realistic sensor simulation with a combination of physics and machine learning. LiDAR generates point clouds by shooting light into the scene and measuring the travel time to determine an object's distance. To mimic this process, we raycast over a scene and generate a simulated point cloud. However, raycasting generates more returns than real LiDAR, since the return light does not always meet the detection threshold in the real world. We call this phenomenon ray drop. Ray drop is complicated to simulate for physics alone because we don't know the physical parameters of the real world. Fortunately, using a ray drop network, we leverage real-world data and machine learning to bridge the sim-to-real gap. We convert each LiDAR sweep into a spherical image representation, encoding features related to ray drop, such as range values, incident angles, semantics, and pulse intensity values. We then feed these features into the network and predict how likely a ray will be dropped. The labels come from real LiDAR ray drop patterns. We sample the ray drop probability to generate the final point cloud. We now show results. Green boxes indicate vehicle detections from a model trained on real data only. This side-by-side comparison shows that LiDAR sim generates realistic point clouds with a small domain gap for downstream perception tasks and autonomy testing. We now compare LiDAR sim against Carla, a state-of-the-art sensor simulator. A model trained on Carla data and tested on real data has a large sim-to-real domain gap. But a model trained with LiDAR sim has just a 1% domain gap, significantly outperforming Carla. The small domain gap means LiDAR sim is effective for data augmentation. By combining LiDAR sim data with real LiDAR, we gain a significant performance boost for vehicle detections with both small and large amounts of data. LiDAR sim also allows us to evaluate a perception and motion planning system maneuvering safety-critical scenarios in a closed-loop setting. Here we see a simulated scenario where a vehicle turns into the DSDNet lane, occluded by a bus. The system, trained only on real LiDAR data, is able to process LiDAR sim data and safety brake to avoid collision. With no additional training or domain adaptation, we can directly use LiDAR sim to test an autonomous system end-to-end on millions of different scenario variations, achieving results that match closely with the real world and allowing us to gain new insights and to test the performance of the safety of our self-driving vehicles. But modern autonomous vehicle car platforms are not only equipped with LiDAR, but also equipped with multiple high-resolution cameras, covering different viewpoints, the front view, side view, and rear view. This means we need to also simulate camera images which are consistent across viewpoints and time. Let's review the standard graphics-based camera simulation, as well as the recent progress in using neural networks for camera sensor simulation. Graphics-based camera simulation relies on classic rendering techniques. On one hand, real-time rendering is cheap and efficient, but does not produce photorealistic sensor data. On the other hand, high-fidelity rendering is very expensive and hence not scalable, as it usually takes a few hours to render a single image. Recent neural net rendering formulates the camera sensor simulation as the process of conditional image generation, either through semantic layer-to-image translation, domain adaptation, and image manipulation. However, these single image-based methods cannot be directly applied to create a virtual environment for self-driving cars, as the simulated camera images are usually geometrically inconsistent. Other methods insert 3D vehicles into the scene by encoding and manipulated semantic image representations, or manually specifying vehicles in new locations and rendering them. However, this requires very expensive manual editing and hence is not scalable. In addition, these approaches do not have a 3D scene representation, making them difficult to extend to video or for handling interactions with other actors in the scene. In contrast, I will present now a novel effort towards photorealistic camera simulation by leveraging existing camera sensor data that, as we saw, we have millions of those miles recorded, and the 3D geometry of the scene, and inserting dynamic objects into the scene in a geometrically consistent and physically plausible manner. We can then create a great amount of scenarios that potentially capture the diversity in the long-tail distribution of driving data. As an example of this, let's play a game. Which of the objects in the depicted images are fake? Did you guess correctly? What you just saw is GeoSim, a novel approach that leverages graphics-based rendering, real data, and machine learning to simulate camera sensor data from multiple points which are geometrically consistent. GeoSim takes advantage of recorded camera data, LiDAR scripts, and 3D bounding box annotations to aggregate the real-world sensor data for dynamic objects encountered in the world. Such data is readily available in modern self-driving datasets. We first used the real data collected to create a large-scale and diverse 3D object bank with precise geometry, high-definition appearance, and accurate 3D poses. To build our assets, we developed a 3D reconstruction network that takes camera and LiDAR sensor input from multiple viewpoints for a given dynamic object and outputs a high-precision 3D shape. Specifically, we process and combine crop LiDAR point clouds and images into a single feature embedding, which we then use to predict the formations to a mean template shape prior. We then perform energy optimization on the predicted shape to make sure it agrees with the input LiDAR and images. Note that we don't require any ground truth 3D shape data. Here are some examples of 3D assets with the corresponding images. Note that we can model vehicles of very different shapes as well as sizes. We then place 3D assets onto the high-definition map so that they reflect the traffic and 3D layout in a realistic manner. Note that our object placement is not only 3D aware, but is physically plausible and temporally consistent. We leverage an intelligent driver model for simulating the vehicle trajectory over time and making sure it has realistic acceleration and braking, such that the full scenario is coherent. Once we have selected an object from our asset and decided where to place it, we use novel view rendering with 3D occlusion reasoning with respect to all elements in the scene to create the appearance of the novel object in the new camera image. Finally, we generate photorealistic camera simulation using a post-completion image synthesis network that adjusts lighting and resource boundary artifacts. Unlike existing work on neural image synthesis and manipulation, which either requires human interaction, is not realistic, or only models it to the context, our approach is fully automatic, photorealistic, and 3D layout aware. We compared the proposed GeoSim with the state-of-the-art 2D neural rendering methods, as well as a retrieval-based copy-paste baseline. Compared to 2D-aware image generation models, such as Pix2Pix HD or guided editing, GeoSim produces much more realistic augmented images with little to no distortions or aberrations. And compared to a simple copy-paste baseline, we can see the value of GeoSim's 3D-aware placement and occlusion reasoning for creating a reasonable image scene, and the effectiveness of the post-completion network to seamlessly fuse the source and target images. We also measure the perceptual realism of the simulated images using FIT. Our method is capable of producing significantly better quality images than other methods. To further verify the realism of GeoSim, we conduct a human A/B test. We show a pair of images generated from different approaches on the same background real image, one from GeoSim and another from one of the competing algorithms. We then ask the human judge to click the one that they believe is more realistic. From over 20 users and close to 5,000 image pairs, we can see that GeoSim images are preferred more than 94% of the time, and even sometimes 99% of the time compared to some of the baselines. This confirms that there is a significant gap between other baselines and GeoSim that is immediately noticeable. But perceptual quality metrics are not enough. To verify we can use GeoSim for autonomy evaluation, we take perception models trained on real data only and perform inference tasks on image segmentation, 2D object detection, and monocular 3D object detection on the simulated images, and compare the performance with real images. As we can see qualitatively, a model trained on real data can still segment, detect out the GeoSim added cars just like other real cars in the sim. We now show how perception algorithms trained on real data perform on images generated from the different simulation baselines. We first show the results when evaluating on real images. The numbers in the parentheses indicate the performance gain loss using different simulators. Here are the results of the different image generation baselines on the different tasks. We want to emphasize here that a higher IP or mean IOU perception metric on simulated data is not necessarily better. Instead, we want the perception metric to as closely match the performance on real data. This difference is reported in the parentheses. The closer the metric on simulated images matches with real, the more likely the perception algorithm considers the simulated image as from the same distribution as real data it was evaluated on. As we see in the table, there is a clear difference between using real images and synthetic images generated by 2D-based neural in-painting methods. In contrast, perception algorithms trained on real data alone will generate consistent results reflecting the correct semantics in both GeoSim and real data. We now show some more examples of GeoSim. Here's an example of with a simulated object. Can you tell which one is simulated? Notice that we can simulate objects at different and diverse viewpoints, front or back, far away or close. We can accurately handle occlusion with static background objects, other vehicles, and even pedestrians. Even more explicitly, we can extend our geometry-aware image simulation by composition approach to video simulation. Notice that our simulated images are temporally coherent and that the added objects obey traffic and have reasonable motion. Multiple objects can be added to the scene and interact with each other, for example, performing light changes. Being 3D aware also means we can also do multi-camera simulation that is physically possible. We use GeoSim in the next. We hope GeoSim is the next step in providing realistic camera simulation for autonomy testing. Now that we have covered different approaches to do holistic understanding offline of data captured by driving millions of miles, we turn our attention to real-time reasoning that needs to be done online in the vehicle to drive safely and smoothly to its destination. A very popular approach in academia is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements, for example, LiDAR or images, and the output is the information necessary for the self-driving car to drive, for example, a steering command and acceleration. The advantage of such an approach is that it is very easy to get a prototype with just a few lines of code. Furthermore, the system is trained for the end task, which is the task of driving. However, this paradigm has several key disadvantages. It is difficult to incorporate prior knowledge and thus make this system respect the rules of traffic. It also has no interpretability, which poses a problem for the system validation and safety. An alternative is the traditional software stack, which is composed of a set of modules executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's-eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then, the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically every 100 milliseconds. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations, and it's easy to incorporate prior knowledge. However, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes. Furthermore, the different modules are not trained for the end task, and as improvements in model performance do not translate to better driving. Our vision at UberATG, which is different from any other competitor, has the advantages of both end-to-end and traditional engineering approaches, but without inheriting their respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly developer productivity. As computation is now shared across modules, the resultant reaction time is also much lower. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, every improvement results in better driving. In the following, I will introduce 3 efforts from our lab that align with this direction. Our first work is the end-to-end interpretable neuromotion planner, published at CVPR 2019. It uses a DeepNet to produce a learned cost volume and improve the power of the deep network with detection and prediction tasks. Later, we propose DSDNet, Deep Structural Driving Network, which further improves performance and interpretability by outputting a non-parametric multimodal prediction and planning condition on this prediction. The third work investigates how to bypass detection post-processing, which may lose useful information. We propose to perceive, predict, and plan through interpretable semantic representations, where we replace instance predictions with an instance-free semantic occupancy representation and use learn interpretable planning costs over that to produce planning. Now, let me briefly explain the main idea behind each of these works. Here's the model of the end-to-end interpretable neuromotion planner. More specifically, we feed LiDAR and HCD maps into a backbone CNN and extract a feature map. From there, our model decodes detection bounding boxes of actors in the scene, as well as the predicted future motion, as shown on the top right. To conduct planning, the core idea is to generate a cost volume using the convolutional networks. Each channel in this volume represents a future timestamp, and each pixel in the volume represents the cost of traveling to that location at that timestamp. Then we use a physically valid trajectory sampler to sample a wide variety of trajectories given the current ego poise. These trajectories are guaranteed to follow vehicle dynamic constraints. The cost of a sample trajectory can be obtained by indexing the learned cost volume and the waypoints along that trajectory. The minimum cost trajectory will be our final planning output. Importantly, all computations from raw data to the final trajectory can be done in a few milliseconds. We evaluate our approach in our challenging ATG-40 dataset. This dataset contains over 1 million frames from more than 5,000 snippets collected from multiple cities across North America. It provides point clouds from a 64-beam LiDAR sensor and high-definition maps. It contains challenging urban scenes with many actors, making it interesting for interactions and motion planning. Here we show our results. Compared with the state-of-the-art, our model achieves on par or better detection and prediction performance at the time of publication. More importantly, as we can see in the figure, our planning results have a much lower collision and lane violation rate, which indicates safer planning. Here are some interesting qualitative results. In all 4 figures, blue boxes depict detections, red boxes depict the ego car, and the colorful region in the cost is the low-cost region predicted by our model, describing where the ego car should drive. On the top left, we show an example of following lane, and on the top right, we show an example where the ego car encounters an intersection. Here, our model shows nice multimodality. The bottom 2 figures show that our model can navigate along the lanes as well as avoid collisions with other cars. Now let me show you a short demo. Our model takes latent and HD maps as input and outputs detections, predictions, as well as motion planning cost volume. We highlight low-cost regions for different timestamps using different colors. Our planned trajectory is shown in red, and ground truth trajectory is shown in blue. As we can see, it follows the lane perfectly. Note that our cost value captures multimodality. In this case, we can either go straight or change lanes. When approaching an intersection, we can either keep lane or turn right. We can also handle blockages. The cost volume shows a preference to lane change in order to avoid collision. And here are two examples of super nudging into heavy traffic, which is one of the most difficult maneuvers in driving. However, there are still drawbacks. First, planning is not conditioned on the prediction results, which may cause inconsistencies and potentially dangerous planning. Second, the model only predicts a single mode of the future, but the future is actually uncertain. And I'm talking here about the prediction, not necessarily about the motion planning, which as we saw was multimodal. To address these drawbacks, we propose DSDNet, a deeply structured self-driving network that jointly reasons about perception, forecasting, and motion planning. Specifically, our method has several advantages. First, computation is shared between models and thus allows for real-time inference. Second, our method explicitly models socially consistent multimodal uncertainties in the future. And finally, our learning-based planner leverages the power of deep learning and takes traffic rules into consideration, as well as in order to guarantee safety. Now let's have a look at how the model works. Given later point clouds and an HD map as input, we have a neural network to produce background features, which will be shared with other models. We first use such features to predict the detection results. Our next step is to predict the future behaviors of all actors, as well as the uncertainties, which are shown as colorful regions in the figure below. Here, different colors mean different future timestamps. This is a non-trivial task, as we expect to predict a multimodal non-parametric distribution which can capture complex situations. More importantly, behaviors of all actors should be socially consistent. For example, they shouldn't collide with each other. To construct such non-parametric distributions, we first sample a set of dense and diverse trajectories for every actor. Then we use a neural network to predict an energy for each trajectory based on the input data. After normalization, this becomes a distribution. Although we can do this for all actors, we can see here that the resulting predictions are not consistent. For example, two distributions may overlap, meaning two cars will collide with each other, which is not realistic. To tackle this, we propose to conduct message passing between all actors and encode their socially consistent interactions within pairwise energies. This gives us multimodal, socially consistent predictions. Finally, our model plans a safe trajectory with a cost minimization procedure, which ensures the produced planning will have minimal expected collision rate and suits the current scenario. Here we first report our prediction performance. We compare our multimodal socially consistent prediction method against several state-of-the-art methods on a number of datasets. We show the results on two publicly available datasets, in particular, GeoSim and Carla. We achieve significantly better prediction error. Our method also achieves a near zero collision rate among predicted trajectories, which corresponds to more realistic human behaviors. Here we show our planning results. Again, we compare against end-to-end imitation learning methods, as well as our previous NMP method. Our DSD approach achieves significantly better performance in terms of collision and in violation rates. This is due to the fact that now our model explicitly considers multiple future possibilities and then plans a safe trajectory that is compliant with the actor's future behavior. Here we show some interesting qualitative results. We visualize the uncertainty through a dense color map. Different colors represent different time steps. This is the uncertainty at 1 second into the future, 2 seconds into the future, and then 3 seconds. As you can see, our algorithm really captures all the uncertain futures for the car in the circle. Here are some more examples. The top left shows that our model is certain about the vehicle that follows a straight line. Simultaneously, it is also uncertain about a faraway vehicle that is turning. The remaining 3 figures show some interesting driving behaviors, such as perfectly following a curved lane, turning left, and nudging around a parked car. Here is a short demo of our model. As you can see, our model nicely captures multimodality, especially for vehicles that are approaching an intersection. When a vehicle is driving in a straight line, our model is certain about its direction, but uncertain about its future velocity. Here is an example where we perfectly predict that the leading vehicle is stopping, and we plan a nudging trajectory to avoid collision with the parked car. As this shows, our model can follow the lane perfectly. And that's the nudge. So far, we have discussed 2 efforts on how to improve interpretability. Both of these works detect surrounding actors first, and then conduct planning based on detection and prediction results. For example, in this case, the ego car will know a coming vehicle is crossing its left turn lane, and thus yield to the car. However, detection requires post-processing, typically NMS, and only reflects an actor if its detection score exceeds a certain threshold. But what if the detection score flickers a bit and then suddenly is below the threshold for this car? In some cases, this will cause a very severe collision. Therefore, just relying on detection like this is not necessarily safe. To address this, we propose to perceive, predict, and plan through interpretable semantic representations. Rather than performing object detection and then predicting trajectories for each object, this model directly generates semantic future occupancies. Furthermore, the occupancy forecasts are scene-based and instance-free, and hence do not require thresholding of detection scores or performing NMS post-processing. The planner uses these non-parametric spatiotemporal occupancy maps, along with other interpretable costs, to plan a trajectory that is safe, comfortable, and respects traffic rules. Note that the entire model can be trained end-to-end since all the components are differentiable. Let's dive a bit deeper into the semantic occupancy representation. We consider vehicles, pedestrians, and bikes, and as the classes for which we want to predict this occupancy. To make the representation more interpretable, we further subdivide these classes semantically as shown in this hierarchy. For example, for any given pixel in the region of interest, we predict how likely it is occupied by a vehicle on conflicting lanes, parked vehicles, or any other semantic classes. In terms of the inference process, we take data strips and an HD map as input and extract backbone features with a two-stream CNN network. Then a recurrent occupancy update network predicts semantic occupancies into the future. As you can see, there is no post-processing at the actor level. This is beneficial since the computational cost doesn't increase in cluttered scenes and is not a function of the number of actors. Finally, we conduct the planning step. The planner samples a set of trajectories. A cost function is used to evaluate each trajectory, considering different aspects of driving. The best trajectory is then selected for execution. Here we show some examples of our interpretable cost function. For example, the spatiotemporal occupancy maps are used to penalize trajectories that overlap with potentially occupied regions. We use the map data to penalize trajectories that are not close to the lane centers or violate boundaries or do not follow the given route. We also take into account the smoothness and comfort of the trajectories in the cost functions and penalize, for example, trajectories that are turning at high speeds. So as you have seen, the trajectory cost function in our planner considers various aspects of driving. The relative importance of these sub-costs are learned jointly with the rest of the pipeline, including detection, the semantic occupancies. Here are some quantitative results from open-loop experiments. That means that we enroll the predictions and motion plan for 5 seconds into the future without replanning. In other words, in these experiments, the SDV does not get any further observations within the future horizon of 5 seconds. The results show that our proposed model is much safer than the baselines. For example, we get a 40% less collisions than the best baseline through the 5-second future horizon. Also, the generated trajectories of our model are more similar to the driving behavior of humans. In this video, we visualize our interpretable semantic occupancy, as well as our planned trajectory. We unroll our planning into the future as shown with the black solid box, and ground truth is shown with an empty box. We use different colors to indicate different semantics that are predicted by our model. You can see them in the legend. As you can see, our semantic occupancy really captures where the other actors are. And as times go by, the occupancy map changes to provide information of where the other actors will go in the next few seconds. And then our planning can use the interpretable cost to produce a safe and compliant trajectory. Thanks to LiDAR-Sim, our state-of-the-art LiDAR sensor simulation that was just presented as an oral at CVPR 2020, we can further do closed-loop end-to-end evaluation for the planner. We ran 80 challenging scenarios, each of a duration of 10 seconds, with our closed-loop simulator. Those 80 scenarios are particularly designed to test the safety of our decision-making when facing critical situations, and therefore they are extremely difficult. We collected various planning metrics as shown in the table, and compare our method to a method that detects objects and then predicts trajectories. The results show our end-to-end planner is much safer and generates significantly more comfortable trajectories. In conclusion, in the offline setting, we have seen that to even begin understanding our data, we need to first properly store and compress the large-scale datasets. I show recent state-of-the-art algorithms for compressing sensor data by taking advantage of multiple viewpoints and temporal redundancies and entropy coding. Once we handle the storage, we can then begin log understanding of the previously recorded data by generating useful learned representations for a structured question and answer. With our compressed real data and ability to store meaningful representations for mining relevant logs, we can then perform simulation to generate new sensor data for better understanding and evaluation of the autonomy system. With the offline setting providing support, we can improve our perception and planning algorithms' understanding of the world and perform safer self-driving. Most of the material shown today is new and has not been shown before. Stay tuned for a series of archives revealing all the details of this work that we have shown you today. This is all from me. Thank you very much.